Alrighty. Let's get started. Can you hear me in the back? Yes? Fantastic. Okay, no technical difficulties today, at least not at the start, so we're going to get started on time today. Okay, so today we're continuing on our journey of linear classifiers. What have we seen so far? So we've seen LDA, linear discriminant analysis, as a generative model, right, for classification. Logistic regression, the discriminative model. We actually haven't yet seen perceptrons, or the perceptron learning algorithm. We'll cover that at the beginning of today's class. We didn't quite get to it last time. Which also means, by the way, that actually the slides that I'm presenting are like very slightly different at the beginning from the slides that were on Piazza. Hopefully no one gets super tripped up by that. But really this week what we're going to be doing is diving deep into one of the most classic machine learning models that people, less so these days, but is still very important to know about for classification, which is the support vector machine, or the SVM. Okay, and so we're going to be taking a break from probability, probabilistic models, MLE, map estimation. But before you get too excited about that, you should know that SVMs approach this classification problem from a different perspective that's, equally, if not more, mathematically rigorous, which is the geometric perspective. So get ready for, lots of linear algebra and stuff like that. It's still going to be fairly confusing. And today we're going to cover the most basic formulation of the SVM, which is known as the hard margin SVM. And we'll explain today and Wednesday what that means and why people call it that. But actually, let me start with a slide that I think that you don't have in this slide deck, although it is in last Friday's slide deck, on linear classifiers and what that even means in the first place. So remember, for binary classification, right, we can write linear classifiers as essentially making decisions based on the sign of the model's output. So remember, what is a classifier? It's a model plus a decision rule, right? So my model could be something like a probabilistic model, and then my decision rule could be like predict the class with the highest probability. But in general, I could have non-probabilistic models too. Things like, my model is just, some linear model that outputs a number. And then my rule is predict 0 or 1 based on the sign of whatever my model output. And it turns out all linear classifiers, including logistic regression like we saw, can be written in this way, right? And then this line, the set of all x's such that theta transpose x equals 0 is referred to as this separating hyperplane, right? More generally, we could have, these decision boundaries that might be nonlinear if we have more complex models. But for the linear case specifically, we call it a separating hyperplane, which is one instance of a decision boundary. And so logistic regression, right, is a probabilistic view of this particular problem, and it allowed us to use tools like MLE, map estimation, and then formulating things such that they were amenable to gradient descent in order to learn the theta that best explained the data. Today, we're going to instead see a geometric view of this problem, which leads to a model and an algorithm known as SVMs. Okay, and we're going to dive into some pretty gory mathematical detail behind how SVMs actually work. But let's actually start by looking at another very simple algorithm known as the perceptron learning algorithm, which I think will set us up nicely into the motivation behind why we want to look at SVMs in the first place. Okay, so let me tell you about one version of this algorithm known as the perceptron, and it's basically the simplest version that you could imagine. So the perceptron is an algorithm for learning theta, right? It's an algorithm that says, given a bunch of data, xi, yi, right, learn a theta that is a good model for binary classification for this data. And it does the following. It's basically repeating the following update to my parameters theta. So it's an iterative algorithm, right, where I start from some theta, and then I'm repeatedly going to be doing the following update. I pick some data point, xi, yi. Maybe it's random, or maybe I'm just looping through all my data in order. It doesn't actually really matter. So I'm going to pick a data point, and then I'm going to say, did my model classify this data point correctly? Is the sign equal to the sign of yi? If so, don't do anything. Just keep going. Pick the next data point. If not, if my model was incorrect, then I update my theta according to xi where yi tells me the sign in the direction in which I want to go, right? Oh, you know what? I actually just realized one thing. So I should have put it on this slide, but here, so what did we have before when we had logistic regression? Yi's were either zeros or ones, right? Here, yi's are actually negative ones or ones. Okay, so they represent a particular sign. Okay, like the negative class versus the positive class. Okay, that is an important distinction. Otherwise, this math doesn't actually make sense, right? But you know, that's just how we define the problem. It doesn't really matter too much. It's whatever is convenient, right? Is 0, 1 convenient, or is negative 1, 1 convenient? For logistic regression, 0, 1 was convenient. Here, negative 1, 1 is going to be a little bit more convenient, just in terms of how easy it is to write out all the updates. Okay. So anyway, we repeat this process until my model correctly classifies all of the data points that I'm given, all of the xi, yi's. This is not an obvious statement. But for linearly separable data sets, which means that for data sets where there is some theta that correctly classifies all of my data points, we will eventually converge to that theta, to a theta that is correct on all of my data. However, if the data are not linearly separable, which means that there's no line that I can draw that makes it perfectly distinguishing between the two classes, then this algorithm is actually never going to converge. It's just going to keep running forever and ever and ever, and it's not actually ever going to return you a theta that it's satisfied with. So why is this cool? Well, it's actually one of the earliest examples of a learning algorithm, an algorithm that takes a bunch of data and then returns parameters that represent a particular model that fit that data, right? And also, if you look at it closely enough, if you look at this update rule, it has some kind of interesting similarities to this stochastic version of the gradient update for logistic regression. So you can go back to Friday's slides and see how they kind of compare to each other, but there are some kind of interesting connections that you can make there. But here's another example, right, of how I might be able to learn a linear classifier. We've seen logistic regression, right, MLE, map estimation, that's how we get theta there. But turns out there are other ways that we could approach the same problem, right? And we could approach it directly from an algorithmic point of view using something like perceptron, which basically is just a procedure, right, that given a bunch of xi, yi's will return me a theta, hopefully, right, if all the data are linearly separable, that correctly classifies all of those data points that I'm given. So then one question that we can ask is, what does the perceptron learn? So this algorithm takes a bunch of data, for example, these green O's and these red X's, and then it returns a theta, which represents a decision boundary, a separating hyperplane, right? Something like this blue dotted line, right? And I told you that if the data are linearly separable, then it will return some theta that is correct. But in general, for all of these problems, we actually have like an infinite number of theta that are correct, right? Like I could have, this one, this blue dotted line that's already drawn. I could also have some other ones, right? Like I could have this one, right? Here's another, drawing errors aside, here's another like decision boundary separating hyperplane that correctly classifies all of my data, right? And then I could also have, something like this, right? Like these are all possible theta that the perceptron algorithm could return to me, and it depends on things like how did I initialize my theta, right? Do I randomly sample my data as I go, or am I going through it in order? What order? All of these things actually end up mattering in terms of which theta you're actually going to get back from the perceptron algorithm, okay? So in general, for perceptron, there are no guarantees about which decision boundary, which separating hyperplane is going to be learned. But if we look at some of these boundaries, it kind of does seem like, at least maybe intuitively, we could say that maybe some kind of seem better than others, So we might intuitively be able to say, well, actually the one that was originally on this slide, it kind of seems better than the two that I just drew onto there, okay? And so we're going to try and analyze this intuition a little bit more, try to figure out why that might be the case, right? And then try to, figure out if there's a better way that we can try to learn the decision boundary that we think is best for some definition of best. That's what we're going to try to figure out today, okay? Okay, so then what is a good decision boundary? Well, there's not any one single answer to this problem, right? And then sort of baking in your assumptions about what you think is the answer to this problem is kind of part of the magic behind machine learning, right? It's about defining the model that you think fits best. So, for example, logistic regression answers this question from a probabilistic viewpoint, right? It says that a good decision boundary, or the best decision boundary, is the one that maximizes the probability of my data based on the probabilistic model that I've put on my data that I assume is the generating process, right? And then this comes down to something like MLE or map estimation, which then gives me the procedure for figuring out, what that decision boundary should actually be. What we're going to learn about today are SVMs, right, which instead answer this question from a geometric viewpoint. What do I mean by that? Basically, SVMs consider the distance to the boundary from the closest points to that boundary. Okay, so for example, here, what's a good color? Here, my closest points are like this one, and then I can consider this distance, right? But then I also have some points on the other side that kind of look like, they kind of have the same distance to this boundary, right? The reason that it's called SVM, by the way, is because the points on either side that are closest to this boundary are called the support vectors. We're going to see exactly why they're called the support vectors, but that's why this thing is called the support vector machine, SVM. Okay? SVMs are considering the distance from the decision boundary to the closest points to that boundary. And this distance, sometimes times 2, based on whatever convention you're using, this distance is called the margin. Okay? The margin is the distance between points on either side of your hyperplane to the hyperplane. Or if you multiply that by 2, then the margin would be the distance between the points, right, on either class. And then what support vector machines say is that you should find the decision boundary that maximizes the margin, okay? Try to maximize the distance from the boundary to the closest points on either side. Okay, so that's at least the high-level definition of what SVMs are trying to do. Okay, and we'll try to draw that on the next slide. But are there any questions about the definition itself? Yes? So are we finding the decision boundary that maximizes the margin from just one side or from both sides, right? So it's from both sides, right, which means that the decision boundary that maximizes margin is going to be in the middle, right there between the points, right? Because that's the way that we would maximize the minimum distance from any points on either side, right? Okay, let's try to visualize a little bit what this max margin linear classifier actually is. So remember, we already drew the margin over here, right? For this particular decision boundary, right? The margin would be like this distance, the norm of like this orange line that I'm drawing here, right? And then, this is an approximate drawing, but we're kind of assuming here that these two red points kind of lie the same distance away as that green point. So this is the margin, right? Like these all have these 3 points, which we call support vectors, right? All have the same distance to this decision boundary, drawing errors aside, right? And then the length of that line, this orange line that I'm drawing, would then be the margin, which is what we're trying to maximize, right? So then what does that actually mean? Well, what if I drew, like a decision boundary that looks like this? Well, then what's the margin? Well, now my closest points are like this one, right? And this one right here, right? And you can see that this margin is quite a bit smaller than this margin, right? So that second decision boundary that I just drew has a smaller margin than the first one that I drew, right? And so the first one, probably is at least closer. It probably is the max margin classifier. And the second one is a decision boundary that's valid. It does separate all the data that I have, but it has a smaller margin. And for some reason, we kind of intuitively feel like that one is probably a little bit worse. Why might it be a little bit worse? Well, it comes down to what we care about in machine learning, which is generalization, right? And this is going to be a rather intuitive argument, so if you don't agree with it, that's kind of okay too. It just happens to be the case that in practice this is oftentimes true. But when we're thinking about generalization, we're talking about how does our model do on new data points that wasn't in our data set, wasn't in our training data, right? Well, let's say that I get a new data point that's like out here, or something like that, right? I'm gonna denote it with a purple star because we're sort of saying that we don't know what class this data point actually belongs to. It could be a green circle, could be a red X, we don't really know, right? Well, intuitively, we might say, well, this purple star kind of looks like it's probably a red X, right? It's kind of close to all these points over here, right? It seems like it lies on this particular region of the space. And we can see that our max margin classifier, right, is going to get that point correctly. It's going to say that it's a red X. Whereas this other, decision boundary that we could learn, which does not maximize the margin, right, it would predict a green circle, right? And so what we're saying here is that max margin, because it does the best job at maximally separating these different classes that I have, should be the most reasonable in terms of then generalizing to new test points that we might get. Okay, so that's the high-level intuition behind why we might care about something like a max margin classifier in the first place. It's kind of a geometric viewpoint on what is the best classifier. Okay, this is just one particular answer, but as it turns out, it's a very good answer because it's, SVMs are a very successful model for a lot of different types of machine learning problems. Yes? Is there a similar idea to nearest neighbor classification? Interesting question. So the intuition here kind of seems similar to nearest neighbors, right? Where we're kind of saying like this purple star seems like it kind of keeps the company of these red X's, right? So therefore we would think that it would make the most sense to predict red for this particular point, right? I don't know, I don't off the top of my head know exactly how well that translates into max margin classification, but I would agree that this intuition here kind of seems to build off of that foundation. Yeah. Yes?
When you say margin, are you referring to the distance between the closest point to the boundary? Or?
Yeah, so the margin is the distance from the closest point to the boundary. Yeah, that's correct. On either side, right? So it's going to be symmetrical for the two classes. Yes? Oh, okay. It's not a bad time for questions because it only gets more confusing from here. Unless you're really mathematically inclined, in which case you might actually like the rest of this lecture, but we'll see. Let's actually set up the, oh, yes, sorry, go ahead.
Would it ever get to the point where like it's perpendicular to what like it intuitively should be, but because like going through all the different points, like very minimizes it? Does that make sense?
Do we ever get the case? Well, yeah, so is it ever the case that like maybe our data set's really weird, maybe we have some outliers, something like that, and then because we're trying to maximize this margin, we get something that looks intuitively like it might be kind of wrong? That is possible. We will talk next lecture about how we might be able to fix that. Yeah. Yes?
Is there a reason why not all the points are considered, besides like maybe it's too computationally expensive? Is there a mathematical or
Is there,
reason?
oh, okay, so is there a reason why not all the points are considered? So that's a great question. So I would say, technically speaking, all the points are being considered because you're taking like the minimum distance to the boundary over all of your data points, right? As it turns out, it's just these three data points that have the minimum distance, but in some sense, all of the data points were considered when we were trying to go through this process, right? There is, however, a very interesting mathematical reason why we're only going to need information from our support vectors in order to actually perform our classification. And that's also a big reason why it's called support vector machines, but more on that will come on Friday once we set some of the groundwork first. Yes?
How many support vectors on either side get considered? It's like technically there's only one that's like the very least distance.
how many support vectors do you have to consider? That's a great question. It's at least 2, right? Because there's going to be at least 1 on each side, but there could be more, right? Like for example, for this boundary, there's 3. In general, you can actually have as many data points as you have, right? If they're all sort of like the same, if they all sort of lie on the same band, right? That's very unlikely, but it is possible, right? So I think in general, there's not a very clean answer to how many support vectors there are. Yes?
How do you decide which support vectors to use? Like for different boundaries, there must be different closest points.
Yeah, how do you decide which support vectors to use? So SVMs would tell you that the best decision boundary is the one that maximizes the margin, right? There's one decision boundary that maximizes the margin, and it has a certain set of support vectors that go along with it, right? There are other decision boundaries that will have other support vectors, but they don't maximize the margin, so SVMs don't care. So it's sort of like choosing the support vectors and the boundaries together. That is correct. They're actually what we call a primal and a dual formulation of the same problem, and we'll see more of that on Friday. Yeah. Yes? Oh yeah, great question. So for the 2 red points, right, I am assuming that these are exactly the same distance away from the decision boundary, right? And there is a good reason for that, because if I took this decision boundary and I tilted it like in one way or the other, right, that makes one of the red points closer and the other one farther. And if I'm only looking at the minimum, right, then I only care that I made that distance bigger, right? So there's actually a very good reason why there would usually be more than 2 support vectors. Would you ever use the top 2 or 3 closest? So that's a good question. I'm not aware of anything that does that, but it might be an optimization problem that's very hard. But it might be possible. It might just be difficult to solve. That might be the main issue, yeah. Okay, the SVM problem setup. How do we find the max margin linear classifier? That's going to be the thing that we're going to be trying to do, right? Finding the theta that corresponds to this decision boundary that maximizes the margin, the distance on either side from the closest points, right? So remember that our decision boundary is defined as some linear equation, right? We can say it's W transpose X plus B equals 0. We're actually changing this notation compared to what we had previously, where we just had theta transpose X equals 0. These 2 are equivalent, right? Because what I could do is I could add a 1 to the end of my X, and then put the B at the end of my theta, right? And then these things would all check out to be the same. But as it turns out, explicitly pulling out the bias term B is going to be important for the SVM formulation, and we'll see that in a little bit. So just a notational change. Don't be too confused, right? It's just the same thing that we had before, just written slightly differently, okay? And we are given our data set just like we were before, n data points, right, xi, yi, where all the yi are either -1 or 1. And so you already actually saw this change, right, because it's also the same case for perceptrons. But basically, now our negative examples are labeled as -1 rather than 0, like they were for logistic regression, right? And this is all just like for, convenience, right? I could have whatever labels I want, but as it turns out, for some problems like logistic regression, having a 0 is convenient for the formulation, right? Whereas for this problem and for perceptrons, it's going to be convenient to have those as -1 instead. Let's actually talk about how we calculate the margin. Okay, so if I have a particular decision boundary, right, a particular setting of W and B, how do I actually compute what the margin is for that decision boundary to the closest points? Okay, how do we calculate the margin for some setting of our parameters W and B? Let's drop the whole minimum stuff for a second, right? Let's just consider calculating the distance from some point x to our hyperplane, which is defined as W transpose X plus B equals 0, right? How do we actually find that distance for any point x, okay? Well, the distance, right, from a point to a plane, right, is the length of the vector that is the projection of x, that point, down to the plane, right? That's just the definition, right? And so if we call that projection of x to my plane as xp, and then I can let the vector d be, that vector that spans from xp to x, right? Then what I'm looking for is the length of that vector, the length of d, okay? And then that length is going to tell me what's the distance from this point to this plane. What's the distance from my x to the hyperplane, okay? And we'll draw this on the next slide, but I just want to tell you a couple things first. So we have d, okay, that's the vector, that's the point to the projection. We're looking for the length of that vector. We know one thing that's very important, which is that d, just like my actual weight vector w, is orthogonal to this hyperplane, okay? W is orthogonal to the hyperplane because w defines the hyperplane, right? D is orthogonal to the hyperplane because it's the projection from x down to the hyperplane. Therefore, d must equal alpha w for some alpha, okay? It must be essentially the same direction as w, just scaled by some particular factor, which is what we're going to need to figure out. We also know one more very important piece of information, which is that w transpose xp plus b equals 0, okay? Because xp is on the hyperplane. xp is the projection from x down to my separating hyperplane. Therefore, it lies on that plane defined by all the points such that w transpose x plus b equals 0. Therefore, this particular thing holds, okay? Here are a few definitions that are going to help us get to where we need to go. But we're also going to draw a couple of these things on the next slide just to try to make them a little bit more concrete. So let's draw. Let's say I'm working with two-dimensional data just for visualization, right? So I have x1, x2. And let's say I have some particular hyperplane that looks like this. Okay? So this is, w transpose x plus b equals 0. This is all points x such that w transpose x plus b equals 0, right? And then what I'm saying is I have some particular point x, and I'm trying to calculate the distance from this point x to this hyperplane, okay? Well, this hyperplane is defined by this vector w, right, which we know is perpendicular to the hyperplane itself. It would actually be a little bit more accurate if I drew it starting from the origin, right? Like this is my w, right? It just so happens that, with a b, I can move it around so that it doesn't have to be at the origin. But that's my vector. That's the w. It's the same thing. These two vectors are the same. I just drew them starting from different places, okay? And then what I want to do is I want to figure out what's this distance from x to the hyperplane? What's the length of this purple vector, right? And I get that by looking at this projection xp, okay? And what I know about this thing is that w transpose xp plus b equals 0. That's what I know about it, okay? This d, right, which is like x minus xp, we know is some alpha times w. Okay, this d is equal to alpha times w. And we can see that, drawing errors aside again, that they point in the same direction, they just have different lengths, right? So if we can find w and kind of know the magnitude, if we can find alpha, and we know the magnitude of w, then we have our d. And then we're going to be able to calculate what it is that we want, right? And so we're going to do that on the next slide. But here's a graphical interpretation of all of the text that I gave you on the previous slide. Okay, so these two slides, hopefully together, serve as a good reference for, kind of the intuition behind what it is that we're actually doing. Yes? Why is W perpendicular to the decision boundary? So think that that is a little bit of an involved geometric explanation, but that is a definition. You can take that as a definition if you want as well, that if the hyperplane is defined by this equation, then this hyperplane will be perpendicular to the W that defines it. That is, you know, also it is kind of a useful thing to know. Yeah. Yes.
And also, for xt, just based on how like this is designed, like you can't really see like if there's an angle between the norm vector w z x plus b and like the x, just the distance vector. So like if say x was just like maybe up a little bit more to the left, like maybe where that pink arrow is, would our xt be like the projection of us matching an x down to w?
So if my x was over here, then I would just be doing the same kind of projection down, right, to a different xp, right, which then, you know, corresponds to a different point that still satisfies this equation, right? That's still orthogonal. Like all of these are orthogonal to the hyperplane, right? Which means that, you know, I would then just be computing, you know, the distance of this vector, which kind of would then still look like this vector, right? But maybe has a different magnitude associated with it. Yeah. Yes. Are we treating W as a unit vector? Not necessarily. Yeah. So W could have some magnitude that's not 1. And we're going to have to figure out how to deal with that later. Yeah.
So then when we say that D is equal to alpha W, that alpha is not necessarily the length of D?
Right. So when we say that D equals alpha W, that alpha is not necessarily the length of D. That's correct. Yes. Let's do some solving. Okay, so let's start from W transpose XP plus B. Okay, we know that this thing is equal to 0, but we're actually going to be able to sort of do some algebraic manipulation to make this something more useful. This thing is W transpose, well, what is XP? XP is this projection from X down to the hyperplane, right? And then we call that vector D, right? So D is X minus XP. What does that mean? It means that XP is X minus D, right? I just moved some things around in my equations. So XP is X minus D, okay? And remember we said that D is some alpha times our weight vector W. We don't know what that alpha is, but we know that there's some alpha that satisfies this, okay? And if I write this thing out, right, then I get W transpose X plus B minus alpha W transpose W. I just, you know, distributed the thing inside the parentheses, right, and then reordered some terms. And I know that this equals 0, right, because I started from this expression, which I already know equals 0, just based on its definition, right? So then if I do you know, a little bit of moving things around, then I get that alpha, right, is equal to W transpose X plus B divided by W transpose W. And we know that W transpose W is the same thing as the 2 norm squared of W. So this is what our alpha is going to be. As you can see, it does depend on the magnitude of W, right? But there's this particular form that, you know, is going to be actually quite useful for us to work with. So there's our alpha. We've solved for alpha in terms of W, B, and X. Doesn't necessarily mean that we're done, right? But we are making some progress. What I really wanted to know, remember, was actually the length of D, right? The distance from X to the hyperplane was the length of D, so that's the thing that I'm actually really trying to find, right? So let's find that. What is the 2 norm of D? Well, the 2 norm of D is alpha W, right? So based on the definition of 2 norm, I know that this is equal to the absolute value of alpha times the 2 norm of W, okay, because D is alpha W. And this thing is going to be equal to, well, Actually, alpha has a 2 norm squared of W underneath, right? So if I multiply this by the 2 norm of W, then it's just this square that goes away, right? Because 2 norm of W cancels out in the numerator and the denominator, right? So what I'm going to get is absolute value of W transpose X plus B divided by just the 2 norm of W, not squared. And that is the distance from a point X, right, down to this hyperplane defined by W and B. Which means that my margin is just the minimum over all my data points, all my xi's, right, of this thing, of W transpose xi plus b divided by 2 norm of W. That's my expression for the margin. We're definitely not done yet, but here is one of our intermediate steps that's going to be useful for formulating our final optimization problem. Okay, now let's keep going. Let's actually, now that we know a formula for calculating the margin, right, the minimum distance from the hyperplane to any of my points, right? Now we can actually formulate our optimization. Remember the SVM optimization problem. We can write it as follows. We're trying to find the W and the B that maximize my margin, right? Maximize the closest distance to any points, such that this ST, right? Sometimes people say such that, sometimes people say subject to. I actually don't even know which one it is officially. But what you write after this ST are all of your constraints, right? All of the things that your solution needs to satisfy in order for it to be a valid solution. And what are our constraints here? Well, our constraints basically intuitively can be written as all of my points need to be classified correctly, right? I'm not interested in a max margin classifier that gets my data points wrong, right? That's not the point in the first place. The point is I'm trying to find a separating hyperplane that has all of the data points on the right side of that plane, right? But the one that, while doing that, also maximizes my margin, okay? So this is going to be, at a high level, what the SVM optimization problem needs to be. So let's actually start trying to fill in some of these pieces, okay? So for example, what is the margin? Well, we already wrote it in one form on the last slide, right? It's this minimum over all my data points, absolute value of W transpose xi plus b divided by the norm of W. Okay? We kind of just need to figure out how to write this in a better way, because an argmax of a min of something is just going to be way too difficult to deal with. That's not a fun optimization problem. That's not the thing that we want to deal with, right? And so there's a particular simplification that we can make to this, which confuses everybody, okay? So, I've seen this thing like, dozens of times, and I think now it kind of finally makes some sense, but definitely at least the first few times that I saw it, it made no sense whatsoever. So if you get lost right here, that's okay. I would encourage you to, go and think about it yourself for a while, but I'm going to try to give you some of the intuition behind why this makes sense, and then I'm just going to say, it just is what it is, and at some point, that's the best that I can do for you, okay? So the way that we're going to simplify this expression for the margin is with the following observation. If I multiply W and B by some C that's greater than 0, okay? If I multiply W and B by some c that's greater than 0, can anyone tell me what happens to my margin? Yes. So does it grow by a factor of c? That's it doesn't change at all, right? Because the numerator and the denominator both have the c that show up, right? So my margin actually does not change if I multiply w and b both by c, okay? Can anyone tell me if I do this, what happens to my separating hyperplane? Yes? So does it shift and stretch? That's also part of the question. Think about the definition of the hyperplane. W transpose x plus b equals 0. What happens if I multiply w and b by c? Nothing, right? Because I'm going to get that thing is c times 0, which is still 0, right? So my margin doesn't change. My separating hyperplane doesn't change. Essentially what I'm saying is I can scale w and b however I like. I can make them really, really big as long as I multiply them both by the same thing. I can make them really, really small, right? Neither margin nor separating hyperplane, okay, HP, change. Okay, so these both stay the same regardless of how I scale my W and B, as long as I'm scaling them in lockstep, right? As long as I'm multiplying the same number to both, right? So basically what this means is that there's actually a hidden, what we call degree of freedom inside this expression right here, where this W and this B could be scaled by something, and as long as they're scaled by the same thing, the overall expression won't change because it's sort of like the quotient. It's one divided by the other, right? What that also means, and this is the part that most people find very confusing, is that I can actually define what I want this numerator to be, okay? I can define what I want the numerator to be because all it corresponds to is a particular scaling of W and B that I'm then fixing, okay? But it doesn't actually change, the types of hyperplanes that I can actually represent, okay? So basically, what I'm going to say is I'm going to set the minimum over all my data points of W transpose Xi plus B. So notice here, no denominator, right? What I'm basically doing is I'm setting the numerator to some fixed value, which is going to make things a little bit simpler. And really, the simplest value that I can think of is 1, okay? If I do this, then my margin becomes 1 over the norm, the 2 norm of W. Okay, so I got rid of this whole min over I business, okay? And I did that by sort of exploiting this extra degree of freedom that I have where actually, kind of the scale of this W and B don't matter because my denominator is trying to normalize out that scale anyway, right? But again, if you don't know what the heck just happened, that's okay. I think sometimes I'm still trying to grasp, get my head around this as well. So, it's definitely confusing. But it is extremely mathematically useful to be able to do this because essentially what we just did is we turned a pretty hard optimization problem into one that actually turns out to be fairly easy to solve. Yes? So basically what we're saying is that the margin doesn't change based on different scalings of W and B, right? So do we have to account for W changing in the margin? The answer is no, because if I change W, that results in a change both in my numerator and my denominator. So those two changes, essentially, you can think of as like canceling out, right? Like if I multiply by C, then the C pops up in both, and then it just turns into 1. So we don't have to do anything. Yeah, nothing at all. This was just an extra degree of freedom that we were afforded that we're making use of in order to make our problem simpler. Okay, think about that on your own time. We're going to continue and talk about the constraints part of our problem, right? Which is this notion that we want all of our points classified correctly. What does this mean? Well, remember we were classifying points based on the sign of W transpose X plus B, right? So we want all those signs to be correct, right? All that means is that I want W transpose Xi plus B to be greater than or equal to 0 if the label Yi is 1, right? Otherwise, I want it to be less than 0. I want that sign to be correct, right? If Yi is negative 1. That's basically all I'm saying. I can rewrite this conveniently as just Yi times W transpose Xi plus B is greater than or equal to 0. Why? Well, because I'd be multiplying a negative number by negative 1, the label, right? And I'd be multiplying a positive number by plus 1. So then that gives me a positive number in either way. This is convenient, but actually there's one more thing that we can do, which is based on how we formulated our objective on the previous slide. Remember, we set the minimum, right, of this absolute value W transpose Xi plus B to 1, which means that this thing, at least in terms of absolute value, will never be less than 1. Yi's are always either negative 1 or 1, right? So then I can actually write this as Yi W transpose Xi plus B is not just greater than or equal to 0, it's actually greater than or equal to 1 for all I, for all of my data points, okay? And that turns out to be kind of like the key ingredient that we need in order to complete our SVM formulation. So basically, in the end, what we get is something that looks like, putting it all together, I want to find a W and B that maximize my margin, which, remember, I wrote, it's still here. My margin, right, which is 1 over the 2 norm of W, such that, or subject to, whichever one you like better, Yi W transpose Xi plus B is greater than or equal to 1 for all I. This upside down A is a symbol that means for all, okay, for all I. There's one thing that people often do to make the problem even simpler, which is this argmax over 1, this reciprocal, thing, it's actually still not particularly nice. I can change this equivalently to be an arg min of just the denominator. These two objectives are the same, right? Maximizing over 1 over this thing is the same as minimizing over the thing directly. And then I can perform another monotonic transformation and get arg min of 1/2 2 norms squared of W. And then these are all the same. These are all going to be the same equivalent optimization problem, okay? And this final thing, 1/2 2 norms squared of W, is oftentimes how you're actually going to see the SVM problem portrayed, because it turns out to be the easiest objective to optimize. But they're all equivalent objectives is kind of the important point, okay? One slide, and then I'll take questions during office hours, okay? This is our final objective problem for SVMs, which we already said. This is an example of something called a quadratic program, which is basically an optimization problem where the objective is quadratic, and then all of our constraints are linear, okay? As it turns out, for these types of programs, effective optimization algorithms, iterative optimization algorithms exist. And we won't talk about them because they're kind of complicated, but 127 and 227 do a very good job of covering this if you're so interested. The solution to this quadratic program is going to be our max margin linear classifier, the one that maximizes the distance to any points on either side of our boundary. But actually, this only exists if our data are linearly separable in the first place, right? If we actually had, classes perfectly separated by a linear boundary. And what if it's not? A lot of the times in the real world, we might not assume that that's actually the case. We'll talk more about that next time in our journey deeper into SVM land. Okay, so I'll stop here, and we have office hours now. Thank you.